Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous videos, we explored how heat forms inside a transformer, the role of oil, and which devices are used for cooling. But how can we accurately assess how efficiently a transformer is cooled? What calculation methods do engineers use? And how do modern digital systems help monitor temperature? This module is about thermal process models, digital monitoring, and how to choose the right cooling system. Heat in a transformer is transferred from the windings and magnetic core to the oil, then to the tank walls, and finally to the environment. The main mechanisms involved are conduction, from copper and steel, to the oil; convection, where oil moves through channels due to temperature differences; and radiation, where heat is emitted from hot surfaces into the air. It's crucial that heat is evenly distributed, as overheating hotspots can damage insulation and reduce reliability. Engineers use several methods to calculate thermal behavior. Analytical methods apply simplified formulas based on thermal resistance. Numerical methods, like finite element analysis or FEA, account for complex geometry and heat flow. Transient modeling simulates temperature changes during overloads, switching, or shutdowns. For example, calculating oil temperature rise during a shift from 70% to 100% load over 2 hours might show an increase of 15 to 18 degrees Celsius. Is that critical? It depends on the starting temperature and the type of cooling system. Modern transformers are equipped with advanced monitoring systems. These include oil and winding temperature sensors, load and current meters, and automatic fan or pump controls. All data is sent to a digital platform that creates graphs, alerts, and trends. This makes it possible to detect overloads before they become dangerous, compare actual behavior to design values, and predict the transformer's lifespan. Digital twins take monitoring even further. A digital twin is a real-time mathematical model of the transformer, built using sensor data and analytical algorithms. It allows engineers to simulate transformer operation under different loads, estimate temperatures in hard-to-reach areas, and control the cooling system with higher precision. Unlike traditional monitoring, a digital twin predicts problems instead of simply reacting to them. To choose the right cooling system, several factors must be considered: the transformer's power and load pattern, the local climate, including temperature and humidity, limits on noise and water availability, and the need for redundancy or fault tolerance. For instance, in cold climates, ONAIN or ONAF may be sufficient. In a hot urban area, OFAF with backup pumps is recommended. In a power plant, OFWF with water from a technical reservoir may be the best choice. Now let's look at a practical calculation. Suppose a 200 megavolt ampere transformer is working in ambient air at 40 degrees Celsius. The windings are made of copper, and the cooling system is OFAF. What top oil temperature can we expect at full load? Based on thermal resistance and oil properties, losses are about 1.2% of rated power, or 2.4 megawatts of heat. With good circulation, the oil temperature may reach 90 to 95 degrees Celsius. Conclusion: that's within the acceptable range, but strict control is needed during overloads. Now a task for you. Choose a transformer for a tropical climate, where temperatures can reach 50 degrees Celsius. The load is variable, and there's no access to water. Which cooling system would you choose? And what sensors would you install for monitoring? Share your answers in the comments. We'll review them in the next video. We've now completed our topic on transformer cooling. Today you've learned how thermal processes are calculated, what monitoring systems improve reliability, and how a digital twin can help manage temperature. In the next module, we begin a new chapter. We'll discuss transformer load capacity, overload conditions, and allowable operation modes. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.